This video is in continuation to the previous video, wherein we found the range of the applied force F under which this block on the incline would be at rest. The range of the force F for equilibrium we found in the previous video is this. And now in this problem, we have to find the ratio F2 to F1. And what is F1? F1 is the magnitude of the applied force which just prevents the block from sliding down. And F2 is the magnitude of the applied force F which just enables the block to slide up. So in fact, F1 is the lower end of the range of the force under which the block would be in equilibrium. So this is the equation for F1, and this is the equation for F2. So the block is in equilibrium between F1 and F2. The applied force, when it is less than F1, the block will slide down, and when the applied force is larger than F2, the block will slide up. And therefore, F1 is the force at which the block is just prevented from sliding down, and F2 is the force at which the block is at rest, but slight increase would make it slide up. So we can calculate the value of F1 using the above formula, using this formula, and plugging in the value of alpha equal to 30 and mu equal to 1 upon 2 root 3, we get F1 equal to mg times 1 upon 4, and similarly F2 would turn out to be mg times 3 upon 4. So the ratio F2 to F1 would work out to 3. So as we see that the range of the force, of the applied force in which the block would be at rest, is fairly wide. It's 3 times F1. Now in the second part of this question, we are given m to be 10 kilograms and g as 10 meters per second square, and we have to sketch the graph of frictional force versus applied force. So we shall do that now. So in order to sketch the graph, we should first compute the values of F1 and F2, and it works out to 25 newtons, and F2, which is mg times 3 upon 4, will work out to 75 newtons. We also work out the force mg sine 30, which is the component of the weight along the plane, and that will turn out to be 50 newtons. So this is 50 newtons. So the block is always being pulled down by a force of 50 newton regardless of the magnitude of the applied force. The frictional force maximum value is mu times mg cos 30, and that works out to 25 newtons. Now this is the maximum value, and the frictional force may vary from 0 to this maximum value depending on the value of the applied force. I have already drawn the sketch of the frictional force Fr and the applied force F. The applied force F is on the x-axis and the frictional force Fr is on y-axis. Let us first mark the force values F1 and F2, which is 25 newtons and 75 newtons. So the block is in equilibrium in this range of the applied force. So this is the range of equilibrium. When the applied force is less than F1, the block moves down. So this is the region where it moves down. The block moves down when the applied force is between 0 and 25 newtons, that is F1. And in this region, when the applied force is above 75 newtons, the block will move up. So the motion of the block is in this range of applied force, less than 25 newtons and more than 75 newtons. And therefore, in these two regions, the kinetic friction will be in play. And what is the value of the kinetic friction? It is mu times n. This is n. So the kinetic friction is 25 newtons, and therefore we can draw a line like this and this. Our positive force is in upward direction. Therefore, when the applied force is small, the block is sliding down and the frictional force is in upward direction. The frictional force is positive, therefore it is 25 newtons plus. And when the applied force is very large and the block is moving up, the frictional force will reverse its direction and will be pointing in downward direction, and therefore it is minus 25 newtons. So we draw a line, a horizontal line like this. Now in between 25 newtons and 75 newtons of applied force, the block is in equilibrium, and therefore the static friction will be in play. And the static friction, as you know, varies between 0 and the maximum value of 25 newtons. So let us see how the graph will look like in this region. So when the applied force is 25 newtons, the maximum frictional force is also 25 newtons, pointing in upward direction, and it will balance out the 15 newtons force pulling the block downwards. So since both are equal, the force pulling it down and the forces pulling it up are equal in magnitude, and therefore the block will be in equilibrium. But now suppose the applied force increases to 30 newtons. Now what will happen is that the frictional force would reduce its value from 25 to 20 newtons, so that this plus this put together is still 50 newtons and matches the magnitude of the force pulling it down. And therefore the block will be still in equilibrium, but the frictional force now has reduced its value to 20 newtons. So at somewhere here is the applied force of 30 newtons, and the static friction will reduce its value to 20 newtons. So we'll draw a line like this. Now suppose the applied force increases to 50 newtons. Now the friction force will reduce its values to 0, because 50 matches with 50, the force pulling it down, and therefore the friction force will be 0, and we get this line. So the static friction will reduce linearly from 25 newtons to 0 as the applied force increases from 25 to 50 newtons. Now if the applied force increases to, let's say, 60 newtons, the frictional force will change its direction and will now be equal to 10 newtons, so that 50 newtons of mg sin theta plus 10 newtons of the friction force will now be equal to 60 newtons of the force pulling it up, and therefore the block will be in equilibrium, because the forces pulling it down and pulling it up are matching. So somewhere here at 60 newtons value, the friction force is 10 newtons, but since it is pointing in downward direction, its value is minus. Similarly, if the applied force increases to, let's say, 75 newtons, the frictional force maintaining its direction will increase its magnitude to 25 newtons, so that 50 plus 25 is equal to 75. So the forces pulling it down will match the forces pulling it up, and therefore the body will be in equilibrium. But now the friction force is of 25 newtons level. So when the applied force is 75, the friction force is minus 25 because it's pointing down the plane. So the graph is linearly decreasing from plus 25 to minus 25 in the region when the block is in equilibrium. So that is how the sketch of the frictional force versus applied force look like. I hope you liked the solution of this problem, and thank you for watching, and would be thankful if you click on the thumbs up sign and subscribe to the channel. Thank you.